Hello everybody, this paper is about rotational light clocks. The title of the paper is Rotational Light Clocks and the Visualization of Spins. My name is Tao. It is about rotational light clocks and how this kind of light clock results in the visualization of spin half. The rotational light clock can also be used to solve the twin paradox in Einstein relativity theory. Here we talk about the main points of this paper. The first point is that rotational light clocks are invented and their behaviors are investigated. And the second point is that a light clock is abstract as a system composed of two distinct points. The 2 points represent the 2 measures of the clock. For a two-dimensional rotational light clock, the 2 measures rotate around a common point. And this point is on the straight line connecting the 2 points, representing 2 measures, but it is not on the line segment with the 2 points at the endpoints of the line segment. This means that the common point around which the 2 measures rotate is not between the 2 measures. The third point is that time dilation appears in the two-dimensional rotational light clocks, and the twin paradox in Einstein relativity theory can be explained by this two-dimensional rotational light clock. The fourth point is that for a three-dimensional rotational light clock, it is always perpendicular to 2 planes on which the 2 measures conduct circular motions. And this clock is used to do visualization of spins, such as spin half. And the fifth point is that it is possible for the three-dimensional rotational light clock to cause no time dilation if its angular velocity takes some quantized values. Here it shows a stationary light clock. The photon bounces up and down between 2 measures. In the video, the green color disk represents photon. The blue light segment represents the light trajectory, and the 2 black rectangles represent 2 measures. Okay, here we can see that this kind of pattern construct a light clock. We call it stationary light clock. Here we show a uniform moving light clock. In this light clock, it moved with a constant velocity v towards the right side. Compared to the stationary light clock, the photon has to travel longer in each step, leaving one measure and reaching the other measure. And this longer trajectory causes time dilation. Okay, here we can see that this kind of pattern can construct a light clock. We call it a uniform moving light clock. Here we show another kind of light clock. It is called two-dimensional rotational light clock. The 2 measures rotate around a common point. that is not between the two mirrors. This common point is called center. The center is here. If the center is between the two mirrors, the clock is called the spinning light clock, not the rotational light clock here. This kind of rotational light clock can be used to explain the twin paradox in Einstein's relativity theory. The stationary twin thinks that the rotational twin would find that the amount of the elapsed time in the rotational frame is less than that in the stationary frame after the rotational twin goes back to the starting position after one complete revolution. This means that rotational clock takes more slowly. Here we should keep in mind that the stationary twin thinks the rotational clock takes more slowly, and vice versa. Any one of the two twins thinks the other one conducts a rotational motion, and the clock of the other one takes more slowly. This means rotational motions are also relative, just as translational motions. Here we show a three-dimensional rotational light clock, and this light clock causes no time dilation and visualized spin half. As this light clock moves, it is always perpendicular to two parallel planes on which the two mirrors conduct circular motions. Here we can see this video. Initially, the photon is at the bottom mirror, and it will hit the top mirror after the clock conducts a complete revolution. And then it will go down and hit the bottom mirror after the clock conducts the second complete revolution. So we can see that the clock goes back to its initial state after two complete revolutions. This is called spin half. In video on the left side, it shows the light clock we just talked about. It is a three-dimensional rotational light clock that causes no time dilation and visualized spin half. And in the video on the right side, it shows what shape of the light trajectory is seen by the two mirrors. Here we show that the two mirrors see the curved trajectory of the light ray that leave one mirror and reach the other mirror in each step. So we can see here that the trajectory is curved, so light binding is observed by the two mirrors. Here it shows a three-dimensional rotational light clock that causes no time dilation and visualizes spin 1/4. Initially, the photon is at the bottom mirror and it will hit the top mirror after the clock conducts two complete revolutions. And then it will go down and hit the bottom mirror, and after the clock conducts the second two complete revolutions, so the clock goes back to its initial state after 4 complete revolutions. That is spin 1/4. The video on the left side is just the video we just talked about. In the right side video, we show that at the two mirrors, see the curved trajectory of a light ray that leave one mirror and reach the other mirror in each step. So here we can see that the two mirrors see the curved trajectory. That means light binding is observed by the two mirrors. Here it shows a three-dimensional rotational light clock that I call it time dilation. Compared to the stationary light clock, the photon had to travel longer in each step, leaving from one mirror and reaching the other mirror. This longer trajectory causes time dilation. In the right side video, it shows that the two mirrors see the curved trajectory of the light ray. The light ray leaves one mirror and reaches the other mirror in each step. So here we show that the two mirrors see light binding phenomena. Here we put four different kinds of light clock together. They include stationary light clock, uniform moving light clock, two-dimensional rotational light clock, and three-dimensional rotational light clock. In this slide, we show how the two-dimensional rotational light clock works. The two mirrors rotate around a common point O, and the point O is here. Two mirrors A and B rotate around its common point O, and geometrically we can see here that the photon initially at B1, and the next step it will go to the position A2. So in the rotational frame, the photon travels longer than it does in the stationary frame. So time dilation happens here. In the stationary frame, the photon travels between B1 and A1. Initially, the photon is at B1, and the next step it will go up to hit the position A1, and then go down, hit the position B1, A1, B1, B1, A1. So this constructs a stationary light clock. However, if the clock rotates, initially the photon is at the position B1, and the next step it will hit the mirror at the position A2, and then to B3, and then to A4, and then to B5. This kind of pattern constructs a rotational light clock. And we denote the two radiuses as R1 and R2. R1 equals OA1, R2 equals OB1. R1 over R2 equals K. K is larger than 1. And R1 minus R2 equals C times delta T1. R1 minus R2 is equal to B1 A1. This is the path for the photon to leave one mirror and reach the other mirror in the stationary frame. R1 minus R2 equals B1A1 equals C times delta T1. Delta T1 is the time interval for the photon to leave one mirror and reach the other mirror in the stationary frame. And we combine the equation 1 and 2 and to calculate the value of R1 and R2. R1 equals K over K minus 1 times C times delta T1, and R2 equals 1 over K minus 1 times C times delta T1. And in the triangle OB1A2, this triangle OB1A2, according to cosine law, we have the equation 5. B1A2 squared equals OB1 squared plus OA2 squared minus 2 times OB1 times OA2 times cosine this angle A2OB1. And we also know that OA2 equals R1. Here we can see OA2 equals R1 and OB1 equals R2. Here we can see the OB1 equals R2. And B1A2 equals C times delta T2. B1A2 equals C times delta T2. B1A2 is the path for the photon to leave one mirror at B1 and reach the other mirror at A2 in the rotational frame. Plug 6, 7, and 8 into the 5, and we can have the relationship between delta T1 and delta T2. And this relationship is shown in the equation 9 here. This slide shows how the three-dimensional rotational light clock works. If the clock is at a stationary state, initially the photon is at B1, and the next step it will go up to hit the position A1 and then go down to hit the position B1 and then A1, B1, A1, B1. This kind of pattern constructs a stationary light clock. However, if the clock rotates, initially the photon is at the position B1, and the next step it will hit the mirror at the position A2, and then to B3, and then to A4. And this kind of pattern constructs a rotational light clock. The radius of the circle, this circle is denoted as R. So here we can see R equals OB1, equals OB2, equals OB3, and equals OB4. And in the triangle B1, B2, A2, B1, B1, B2, A2, according to Pythagorean theorem, we have the equation 1, A2B1 squared equals A2B2 squared plus B1, B2 squared. And we also know that A2B2 equals C times delta T1. A2B2 is here. We can see A2B2 is the path for the photon to travel between the two mirrors in the stationary frame. And C is light speed. Delta T1 is the time interval for the photon to leave one mirror and reach the other mirror. And also we know that A2B1 is C times delta T2. A2B1 is here. A2B1 is equal to C times delta T2. Delta T2 is the time interval for the photon to leave one mirror and reach the other mirror in the rotational frame. Here we can also see that in the triangle B1OB2, this triangle B1OB2, according to cosine law, we have this equation 4 at B1 B2 squared equals OB1 squared plus OB2 squared minus 2 times OB1 times OB2 times cosine this angle B1 OB2. This angle B1 OB2 equals omega times delta T2. And OB1 equals to R, OB2 equal to R. So B1 B2 squared equals R squared plus R squared minus 2 R squared multiplied by cosine omega delta t2. And we write R is proportional to the value of C times delta t1. The proportional constant denoted as K, where K is a positive real number, and combining 4 and 5, we have the following equation 6 to calculate the B1, B2 squared. And here we have B1, B2 squared equal to times K squared times to C squared times delta T1 squared times 1 minus cosine omega delta T2. And then plug 2, 3, and 6 into 1. We have the relationship between delta T1 and delta T2. And this relationship is shown in the equation 7 here. Delta T1 and delta T2 are the time interval for the light ray or photon to leave one mirror and reach the other mirror in the stationary and rotational frames respectively. Here we show at quantized values of the angular velocity cause no time dilation in the three-dimensional rotational light clocks. From this formula 7, we can see that if no time dilation, it means delta T1 equals delta T2, and letting delta T1 equals delta T2 in the above equation 7, then we have 1 minus cosine omega delta T2 equals 0, and then we have cosine omega delta T2 equals 1, then we have cosine delta T2 equals 2n pi. N is a positive integer. So from the equation 10, we see that if the angular velocities were assigned quantized values, there would be no time dilation. It has been shown how rotational light clocks work, and it is possible for clocks in non-inertial frame, such as rotational frame, to take as quickly as they do in stationary frame. Ergodicity may be right. The elapsed time may be same for observers in stationary and moving frame. Time dilation may not happen in moving frames. Here shows the two-dimensional rotational light clocks with different angular velocities omega 1, omega 2, omega 3, and omega 4. And omega 1 is smaller than omega 2, and omega 2 is smaller than omega 3, and omega 3 is smaller than omega 4. And we can see here that as the angular velocity change, the light trajectory marked by the blue color line also change. This shows the three-dimensional case. Three-dimensional rotational light clocks with different angular velocities. And here we can see that as the angular velocity changes, the light ray trajectory changes accordingly. Thank you.